having flights coming very near this geomagnetic pole, especially flights between US, between North America and Europe. So such routes become dangerous after a major solar flare. So in such a situation, the airlines companies often have to reroute their flights, costing much more in aviation fuel and taking much more time. So because of these concerns, the one question is that can we figure out when more solar disturbances are likely to occur on the sun? So as I pointed out that the solar flares occur above sunspots. So when the sun has more sunspots, that is the time when more solar disturbances are likely to occur. So now here is a plot how the number of sunspots seen on the surface of the sun, how that number has varied with time during the last 400 years or so. So the entries just after 1600 were based on the records left by Galileo and his contemporaries. But after that, there was a period of about 90 years when sunspots were not seen at all. And after that, sunspot number has gone up and down in a roughly periodic fashion with an approximate period of 11 years. So this 11 years sunspot cycle was first discovered by Schwabe in 1844. So since we have lots of solar flares or disturbances during the during the peak period of a sunspot cycle, so one can say that this sunspot cycle has become the third most important natural cycle for us after the day-night cycle and the cycle of seasons. There are also some indications that the sunspot cycle affects the Earth's climate, though so far we understand very little how this happens. There are evidences that during the mundane minimum, the Earth was somewhat colder than the usual. Of course, that was before the regular record keeping of temperatures began, but that was an era when landscape painting was very popular in many countries of Europe, and some of the this and some of the landscape painters have left behind paintings of frozen rivers and canals which do not freeze nowadays. So even during the Monday minimum, even the River Thames near London used to freeze quite regularly during the winter, which does not happen now. So it was certainly like a little ice age. And now it's perhaps I can take a commercial break and tell you that I have written a popular science book in which I have tried to give a non-technical exposition of the phenomenology and the physics behind the sunspot cycle. So it was published by Oxford University Press about a decade ago. And since it was printed in UK, so perhaps the price is a little bit high for Indians, but at least Amazon India is selling a Kindle edition at a price which is perhaps not unaffordable. And this our subject began in this year 1908 when astronomer Hale took the spectrum of a large sunspot and found the evidence of Zeeman splitting of spectral lines, from which he concluded that sunspots are regions of strong magnetic field of about 0.3 Tesla, approximately 5,000 times stronger than the magnetic field near geomagnetic poles. So this was a momentous discovery in the history of physics because this is the first time somebody conclusively established the existence of magnetic fields outside the Earth's environment. Now we know that magnetic fields are ubiquitous in the astronomical universe. Most stars, planets, and galaxies have magnetic fields. And also with this discovery, it became clear that the 11-year sunspot cycle is essentially a magnetic cycle of the sun. And about a decade later, Hale and his collaborators made another important discovery. So often two large sunspots are seen side by side, as you see here, with the size of the Earth indicated here. So some of the large sunspots are so large that the whole Earth can be immersed in it. And Hale et al. Found that in the cases of these pairs of sunspots appearing together, usually one of them has a positive magnetic polarity and the other negative magnetic polarity. So the most plausible explanation for that is that there must be some strand of magnetic field poking its nose through the surface in this manner. So if the two intersections become the two sunspots, then in one sunspot you have magnetic field lines coming out, making it a positive polarity sunspot, and in the other you have magnetic field lines going down, making it a negative polarity sunspot. And if this is the case, then we would expect the solar corona to be full of these kinds of magnetic loops above sunspot pairs. And now we know that to be the case. So during the last few years, solar astronomers have invented ingenious techniques for imaging these magnetic loops in the corona. So here you can see a beautiful photograph of some loops in the corona. Now I show you something which I find absolutely fascinating, a magnetogram map of the solar disk. A magnetogram is an instrument with which we measure the magnetic field at every point in the solar disk. If the magnetic field is positive, then white color is put there. If the magnetic field is negative, then black color. And if the magnetic field is too weak or undetectable, then gray color. So here in many places you see a white patch and a black patch side by side. So these are nothing but a pair of sunspots. Since one of them has positive magnetic polarity, it appears in white, and another appears in black because of its negative magnetic polarity. And you may note that in the northern hemisphere, in such patches you have the white or positive polarity sunspot to the right and black or negative polarity sunspot to the left. And in the southern hemisphere, it is opposite. There, black is to the right and white is to the left. And things remain like this for one sunspot cycle of 11 years. If you were to make a magnetogram map 11 years earlier or 11 years later, then you would find that in the northern hemisphere, black would come to the right and white would go to the left, and a similar reversal in the southern hemisphere. So if you just look at the sunspot number, you may think that there is a period of 11 years, but if you also look at the polarity of the direction of the magnetic field, then you have a period of 22 years before the magnetic field comes back again to its original configuration. So there is another interesting thing to note here. If you draw a straight line connecting the centers of these two sunspots, you will find that the straight line would be nearly parallel to the sun's equator, but not exactly parallel, with a tilt. And it is found that sunspot pairs at higher latitudes have larger tilts, even though there is quite a lot of statistical scatter. So it is called Joy's law that sunspot pairs have tilt, and this tilt increases with latitude, named after the discoverer Joy. So here is a figure from here is Joy's original plot showing how he found the tilt of sunspot pairs to vary with latitude. And another thing we note here, so looking at this distribution of magnetic fields, you may feel that underneath the surface in the northern hemisphere, there must be a subsurface magnetic field going from right to left. So if parts of this magnetic field came out to the surface, then you would get positive magnetic polarity sunspot to the right and negative to the left. And in the southern hemisphere, you would have a subsurface magnetic field going from left to right. So in other words, underneath the surface, you expect a sort of a magnetic configuration like this. So in the jargon of our field, this is called a toroidal field, a toroidal component. On the other hand, the Earth's magnetic field is supposed to be like this, which is called a poloidal field or the poloidal component. Now, in 1955, Parker wrote a famous paper in which he formulated what is called dynamo theory, with which he tried to explain how magnetic fields are produced in different astronomical systems. And Parker also gave a model of the 11-year sunspot cycle, suggesting that the model is produced by an oscillation between the toroidal and poloidal fields, somewhat similar to the oscillation between this kinetic and potential energies in a simple harmonic oscillator. So this was a quite remarkable hypothesis for that time, because at that time it was not even known for sure whether the sun has a poloidal field. In fact, in that very year, 1955, Babcock and Babcock, a father and son pair of astronomers, for the first time detected that there is a weak magnetic field near the polar region of the sun with a strength of about 10 to the power minus 3 Tesla, which is much weaker than the magnetic field inside sunspots, which are about 0.3 Tesla. So now the big question is whether there is really an oscillation between these two kinds of fields as Parker suggested. So that question could be answered only after solar astronomers had gathered data about the sun's polar field for several decades. So here is the relevant plot. At the top you see how the polar magnetic field of the sun has varied with time. The solid line indicates the north polar magnetic field, and the dashed line the south polar magnetic field, and below it you can see the sunspot number. So remember that sunspots formed for the toroidal field. So the sunspot number is essentially a proxy for the strength of the toroidal field. And you can see at this time that the toroidal field of the sunspot number was the strongest, while the polar field or the poloidal field was close to zero. And the polar field or the poloidal field was strongest at a time when the sunspot number or the toroidal field was close to zero. So we really see the kind of oscillation between toroidal and poloidal fields which Parker envisaged several decades ago. So now we are in a position to present before you what I would call the central dogma of the solar dynamo theory. So sun's magnetic field consists of both a toroidal component and a poloidal component. The sunspots arise out of the toroidal component, whereas the polar field of the sun is a manifestation of the poloidal component. And in order to have this cycle, this oscillation between the toroidal and poloidal fields, there has to be a process producing toroidal field from the poloidal field, and for the cycle to go on, there has to be a reverse process of producing poloidal field from the toroidal field. So now the job of the aim of the theoretical research in this field to make a proper mathematical formulation of this central dogma. So I shall not be able to get into a full mathematical details of this subject, but I shall try to give you some idea about the nature of the subject. So you all probably know that it was the Indian physicist Meghnad Shah who studied how neutral gas if its temperature is raised to very high values, its atoms get broken and it gets ionized and converted into a plasma. So a plasma is a collection of positively charged ions and negatively charged electrons. And if you put an electric field in a plasma, then positively charged ions move in the direction of the electric field and the electrons move in the opposite direction, giving rise to a strong current. So plasmas are good conductors of electric field, of electric current, and certain electric currents produce magnetic fields which can interact with the plasma. So how do you study this sort of interaction between plasmas and magnetic fields? So although the plasma is made up of many particles, for some purposes we can study the behavior of the plasma by regarding it as a continuum fluid. So the branch of plasma physics in which the plasma is regarded as a continuum fluid goes by a somewhat tongue-twisting name, magnetohydrodynamics, abbreviated as MHD. So it basically combined the equations of electromagnetism and fluid mechanics to get the basic equations of MHD. And let me point out one very famous result of MHD, Alfvén's theorem of flux freezing, named after Alfvén, who won a Nobel Prize for his contributions to plasma physics. So what is this theorem? So suppose inside a plasma regarded as a continuum, we have a hypothetical surface through which is associated with some magnetic flux. And because of motions within the plasma, suppose this after some time, this surface is moved from here to there, and it takes up the position A prime, B prime, C prime, which will also have some flux going through it. And Alfvén's theorem, which can be proved from basic equations of MHD, that states that if electrical resistivity is negligible, then magnetic flux is conserved. So in other words, whatever is the magnetic flux passing through this surface ABC, so when it has moved to A prime, B prime, C prime, the same amount of magnetic flux would pass through it, and as I said, that provided the resistance is negligible. So how small the resistance has to be? So one can define an important dimensionless number, magnetic Reynolds number. I show here how it is defined. So electrical resistivity rho appears in the denominator. So if the resistivity is low, then magnetic Reynolds number turns out to be very large, and the magnetic and Alfvén's theorem holds whenever magnetic Reynolds number is much larger than 1. And I also point out that that L size of the system appears in the numerator of the magnetic Reynolds number. So if the system is larger, then magnetic Reynolds number is larger. And it turns out that for laboratory systems, usually magnetic Reynolds number is much less than 1, whereas for astrophysical systems, it is much larger than 1. And for such systems, Alfvén's theorem holds. So let me explain that with a kind of a thought experiment. So suppose we have a chunk of plasma between the pole pieces of a magnet and we move it sideways. Then we try to figure out what will happen in the two situations of a magnetic Reynolds number much less than 1 corresponding to laboratory, and magnetic Reynolds number much larger than 1 corresponding to the astrophysical situation. So in this Rn much less than 1, nothing interesting happened. So the plasma blobs is moved here and the magnetic field remains as it is. But when magnetic Reynolds number is much larger than 1, as in astrophysical systems, then Alfvén's theorem holds. And we know that whatever flux was passing through this blob of plasma, the same magnetic field flux has to be passed through this blob of plasma. And that can happen only if magnetic field takes up this kind of configuration. So in other words, under this high magnetic Reynolds number situation, the magnetic field behaves like a plastic material which can be bent or twisted by suitable motions of the plasma. And there is a symbiotic relation between MHD and solar physics. So there are many solar phenomena which require MHD for their explanation. On the other hand, some of the most interesting predictions of MHD are for high magnetic Reynolds number situations which cannot be tested in the laboratory. So one often says that the sun is the best laboratory for testing high magnetic Reynolds number MHD. Well, just as the Earth rotates about its axis in about 24 hours, the Sun also rotates about its axis in 27 days. But there is one big difference. The Earth rotates like a solid body, whereas the Sun has what is called differential rotation. In different regions of the Sun, the angular velocity can be different. For example, a point near the Sun's equator takes about 25 days to go around the rotation axis of the Sun, but a point at higher latitude may take more than 30 days to go around the rotation axis. And now suppose there is a colloidal magnetic field line in the Sun, and because of this more highly rotating plasma, this magnetic field line is expected to be dragged out in this fashion, and so that after some time a toroidal field is produced. Exactly, exactly like what was happening in this thought experiment. And even though initially you had just a colloidal field, now you see that there is a toroidal field which has opposite sign within the two hemispheres. So somehow if this toroidal field could float up to the surface, then because of their opposite signs in the two hemispheres, you would expect sunspot pairs in the two hemispheres to have opposite magnetic polarities. Exactly what you saw in this magnetogram map a few minutes earlier. But why would parts of this toroidal field float up to the surface? So before I come to the reason behind that, let me say a few words about what the interior of the Sun is believed to be like. So it has been estimated that the temperature at the center of the Sun is 15 million degrees, and fusion reactions taking place there converts hydrogen to helium, and a very small fraction of mass gets converted into energy by Einstein's E is equal to mc squared equation, and that is the source of heat and energy in the Sun. So up to zero point 0.7 solar radius, we have a region within which this energy or heat is transported outward by a process known as radiative transfer, which essentially means that photons random walk to the stellar matter. But it turns out that from zero point 0.7 solar radius to the surface, this region is unstable to convection, and heat is transported outward by convection. So sunspots are regions of concentrated magnetic field sitting within this turbulent convection zone. So now you can see this image of a sunspot surrounded by convection taking place all around. So why is the magnetic field bundled up in a sunspot like this with very little magnetic field around? To address that question, one has to study the interaction of magnetic field with convection, a subject known as magnetoconvection, of which the linear theory was first developed by Chandrasekhar, and then the nonlinear evolution was studied through numerical simulations by Weiss and many others. So basic idea is somewhat like this. Suppose you hit, uh, suppose there is a vertical magnetic field in a plasma heated from below. So when there is a sufficient temperature gradient in the plasma, that may try to start a convection, but magnetic field lines have tension associated with them, and this tension opposes the convection. So you have to make the temperature gradient sufficiently strong to start convection, and after that, nature finds it expedient to separate space into two kinds of regions. In some regions, magnetic fields are expelled and convection can freely take place, and in the other regions, magnetic fields are bundled up like that, and due to suppression of convection within this kind of magnetic flux tubes, these regions become colder compared to the surrounding regions. So sunspots are believed to be such magnetic flux tubes within which magnetic field has been concentrated by interaction with surrounding convection and due to the suppression of convection within the flux tubes, these tops are colder and darker. And presumably throughout the convection zone, magnetic field exists in the form of flux tubes due to interaction with convection. So now we again come back to the question which we raised a few minutes ago. So if differential rotation stretches a colloidal field line to produce toroidal field like this, then why should a part of it may float to the surface to produce sunspot pairs? So we know that due to interaction with convection, this toroidal magnetic field should remain in the form of magnetic flux tubes with very little magnetic field outside, and we would have to consider this pressure balance between outside and inside of this magnetic flux tube. Outside you have just gas pressure. On the other hand, in the inside you have gas pressure and also magnetic pressure. So the gas pressure inside has to be less than gas pressure outside. So which usually, though not always, suggests that gas pressure inside has to be less than, the density inside has to be less than the density of the surrounding fluid. And Archimedes taught us more than 2000 years ago that such a system tends to be buoyant and rise against gravitational field. So in this present context, this is called magnetic buoyancy, which was first proposed by Parker. And he also showed that the magnetic buoyancy is particularly destabilizing within the convection zone, but it can be suppressed to a large extent below the bottom of the convection zone. So here I show at the bottom of the convection zone with a flux tube like this, and then this part of the flux tube in the convection zone would be particularly buoyant and rise to the surface to produce sunspots in this manner. So whereas these other parts underneath this bottom of the convection zone may remain anchored. So if sunspot pairs are really formed in this way, then we have to study the 3D dynamics of flux tubes in the solar convection zone to understand the formation of sunspots. So it will be like this. So suppose at the bottom of the convection zone, toroidal flux tube is produced by differential rotation. In fact, I may mention that within the last few decades, there has been a remarkable development, helioseismology, the study of solar oscillations, which indicates that there is a region at the bottom of the convection zone where angular velocity changes quite rapidly. So we expect the toroidal flux rings to be produced there. And suppose a part of the toroidal flux ring has come within the convection zone, and then magnetic buoyancy will be strong there, and how it would evolve, that we have to study that through a numerical simulation. And I and some of my co-authors were among the first people to carry on this kind of numerical simulation. So it is essentially an initial value problem. You have to specify some initial value of this toroidal flux ring and then let the simulation go. So at the time when we are doing this work, most of the dynamo theories suggested that the magnetic field inside these flux rings can be at most 1 Tesla. So in this talk, I shall not get into the arguments why it was thought so, but we carried out our first simulations using 1 Tesla, and we found that this Coriolis force is much stronger in this problem than what anybody suspected before. So we found that the Coriolis force overcomes magnetic buoyancy and this flux ring is made to move parallel to the rotation axis to emerge at very high latitudes, whereas the sunspots emerge at much lower latitudes. And we found that only when we make the magnetic field as strong as 10 Tesla, then only we could make the magnetic flux to emerge at the correct latitudes. Now, one interesting question is, now we have discussed about the Joy's law, the tilts of bipolar sunspot pairs. So one interesting question is this. So when this part of the flux tube comes to the surface to produce bipolar sunspots, should we see this kind of tilt presumably produced by the Coriolis force? So that question was first addressed by my first PhD student, Sidney De Silva. So here is a figure from the De Silva Choudhuri paper. So here you see this plot of sign of the tilt of this bipolar sunspots against the sign of latitude. And this solid line is the best fit observational data indicating how tilt increases with latitude. And these various curves are based on our results of our numerical simulation. So you would assume various values of magnetic field inside the flux tubes, and for these various values of magnetic fields, you'd try to find out what would be the tilt at the surface in different latitudes. And we found that we get a good match between observations and theory if if the magnetic field inside the flux tube is taken to be 100 kilogauss or 10 Tesla, and on the other hand, if the magnetic field is either much weaker or much stronger, then we don't have such a good fit between theory and observation. So we were rather happy that nearly 3/4 of a century after the discovery of Joy's law, we were able to give the first quantitative theoretical explanation of Joy's law, and in that process we could put strong bounds on what must be the value of magnetic field in the interior of the sun. Well, I may mention that according to Google Scholar, this De Silva and Choudhuri paper has by now more than 600 citations, making it the most highly cited theoretical solar physics paper entirely from India without any foreign collaborators. Now, as we have seen, if we start from a toroidal field, then by combining these various ideas of flux freezing, magnetoconvection, and magnetic buoyancy, we have been able to explain several aspects of sunspot formations. But unless there is something to keep strengthen the colloidal field, it will eventually decay away and the whole process will stop. And since we have this oscillation between toroidal and colloidal fields, we expect that somehow this colloidal field should be generated from this colloidal field should be generated from the toroidal field, and it's one of the central issues of dynamo theory how this happens. So since this subject is somewhat technical, I shall not get into the details of this subject. But let me just say a few words about this dynamo problem. So I already mentioned that that early solar dynamo model suggested that the magnetic fields cannot be stronger than 1 Tesla. So in this talk, I shall not be able to get into the explanation of why this was thought so. But after this magnetic buoyancy simulation suggested that magnetic field has to be much stronger, like 10 Tesla, then it became clear that we need a new kind of solar dynamo model. and invoking some early ideas of Babcock and Layton, a new type of dynamo model, flux transport dynamo, was developed to explain various aspects of the 11-year sunspot cycle, and some of the this and many aspects of this flux transport dynamo model were developed in our group at IISc. And in fact, this paper, Choudhuri, Schussler, and Dept, is often regarded as the foundational paper of the flux transport dynamo model. So since this is a technical subject, I cannot get into the details of it, and also I have been avoiding the equations in this talk. So for those people interested in mathematical physics who may want to have an idea what the equations look like, so here in one slide I have put the basic equations. The magnetic field can be written like this. So this is the toroidal component, and the colloidal component arises out of the scalar function A. And then you can have time derivative equations both for the colloidal field and for the toroidal field in the form of two coupled partial differential equations. So not much can be done analytically. So in our group, we developed the code Surya to solve this coupled partial differential equation and then make models of the 11-year sunspot cycle. So some of the first results from this code Surya were presented in a paper in Science in 2002. And although I shall not get into the technical details of the flux transport dynamo model, so let me say something about this model which may be of general interest. So so if a sunspot cycle is strong, then we have many solar disturbances during that cycle affecting our lives. So we would like to be able to predict whether a sunspot cycle is going to be strong or weak before its onset. Can that be done with the flux transport dynamo model? So here is a plot of how sunspot number has varied with time in the last few years, and the flux transport dynamo model was developed around this time. So this sunspot minimum was the first sunspot minimum when sufficiently sophisticated flux transport dynamo models were available, and whether these models could predict the strength of the next cycle, that was a very important question. And the first prediction was made by Dept and Zeeman, who concluded the next cycle, counted as cycle 24, would be a very strong cycle. So when going through their paper, I had a feeling that there were certain things wrong with their methodology. So by using a different methodology, we made a calculation with two of my students by using the flux dynamo model developed in our group, and we predicted that the next cycle would be a very weak cycle. So this circle in this axis indicates the time when these predictions were made, and this star here indicates what would be the strength of the cycle 24 according to the prediction of Dept and Zeeman, and this other star here indicates what would have been the prediction of the what was the prediction of the cycle 24 according to our model. So you can see that as time progressed, Sun almost tried to hit our prediction like a bullseye. So in the history of our subject, so this is the first time that a successful theoretical prediction was based on the basis of a theoretical dynamo model. And I will mention that this paper was selected as editor's suggestion in physical review letters as indicated by this symbol. And we are lucky that a few years later, another paper from our group also had this honor of being selected as editor's suggestion in physical review letters. You may know, some of you may know that this is one of the highest honors for a physics paper, And in that next paper, we developed a comprehensive model of the grand minima, like this Monday minima in 18th century, in 17th century, when sunspots were not seen for several years. Well, although I have not gone into the details of dynamo theory, I hope that I have given you some idea of the subject and about about sunspot formation, and also given you an indication of the kind of research which we have done in our field over the years. Now, in the remaining 15 minutes or so, I would like to discuss the solar corona with which I first began my talk, began my lecture. So, although the sun's surface has a temperature about 6,000 degrees, it is inferred that some regions of corona are as hot as millions of degrees. So, this was first realized by Edlin in 1940s. Uh, so how was it found out? So by the beginning of 20th century, solar astronomers managed to take a spectrum of the solar corona, which is somewhat difficult because the spectrum has to be taken during a total solar eclipse, which lasts not more than a few minutes. So when the spectrum was taken, it was found that there are some unknown spectral lines. So initially it was thought that these unknown spectral lines indicated some new element, but by that time, Mendeleev's periodic table was fairly full and there was not any space for a new element. And then Edlin realized that the spectral lines are not for a new element, but are caused uh, by atoms of iron which have lost many electrons, maybe like 8 or 12 electrons. So an iron atom can be expected to lose so many electrons when the temperature is very high. And with the establishment of this high temperature of the corona, these astrophysicists were confronted with another puzzle. So you know about the second law of thermodynamics that which suggests that heat should follow from regions of high temperature to the regions of low temperature. But here it seems that at the solar surface, heat which is going outward is flowing from surface of lower temperature towards a corona which is at higher temperature. So is this a violation of the second law of thermodynamics? So perhaps I shall not answer this question and leave it as a quiz for you people to figure out the answer. And if the corona is really has a temperature of millions of degrees, then from the theory of black body radiation, we expect that quite a lot of radiation would come out and be emitted in X-rays and extreme ultraviolet. Now, our Earth's atmosphere happens to be opaque at this wavelength. So, in order to detect X-rays of extreme ultraviolet from celestial sources, we have to send detecting equipment, instruments in a space mission above the Earth's atmosphere. So nowadays this is regularly done, and we can we have images of the sun in extreme ultraviolet. So here we show images of the solar corona in the extreme ultraviolet from a space mission. So this is certainly not in. Oh, uh, yeah. Okay. Okay, so I'll make it full screen. Okay, okay, and okay, okay, okay. So, so this is certainly not in real time. So you see that the rotation period of 27 days has been squeezed to about a minute or so. And this is a video taken at the time of sunspot minimum and this at the time of sunspot maximum. So you see that the appearance of the corona changes in different phases of the sunspot cycle. The solar surface appears somewhat dark because it's at a temperature of 6000 degrees and we do not expect extreme ultraviolet to be emitted at 6000 degrees. And here you see that the hottest regions of this corona are this sort of loop-like structures, and these are nothing but loops above bipolar sunspots. So whatever may be the mechanism for producing this high temperature of the corona, that mechanism would be most effective in these magnetic loops above sunspot pairs. And certainly the magnetic fields in a coronal loop implies that there must be also currents in these loops. And we know that the current flowing through a metal wire makes the wire heated due to Joule heating. So could it be that the corona gets heated by the currents flowing through the corona? And one well-known result of high school physics is that if you make the same current to flow through a thick wire and a thin wire, then more heat is produced in the thin wire. So when solar astronomers made the estimates, they found that too little heat is produced in the corona if the currents are flow through very wide regions of the corona, but if the same currents are made to flow through very narrow regions of the corona, then one can have sufficient heat production for producing the high temperature of the corona. And in 1972, Parker realized that why that may be the currents the corona may flow through narrow regions. So you may naively expect that the magnetic field of the corona of the loop in the corona would look like that, but underneath the solar surface we have vigorous convection which will distort the magnetic field, so that we expect that the magnetic field would take up this kind of a configuration. And Parker uh, proved a mathematical theorem showing that if the magnetic field has this kind of tangled configuration, then the current is forced to flow through some narrow regions, uh, causing causing the heating of the magnetic flux tube, and eventually the high temperature of the corona. And what causes these solar flares in the corona? So for that, we have to invoke the idea of magnetic reconnection, a very important process in plasma physics. In fact, this process was first suggested when astronomers were trying to build a model of the solar flare. So suppose in the corona we have some magnetic field in a region, and then some new fresh magnetic flux is coming from underneath the surface due to magnetic buoyancy. So it may happen that the old magnetic flux and the new magnetic flux coming due to magnetic buoyancy, they are in somewhat different direction. So there may be a region like this on the two sides of it which magnetic fields are in opposite direction. And if that happens, then from a straightforward application of Ampere's law, one important law of electromagnetism, it follows that in the middle region there will be a strong current density. And since ohmic heating goes as the square of current density, you expect quite a lot of heating there, and this heating may give rise to an explosion. So the solar flares are supposed to be such caused by magnetic reconnections taking place in gigantic regions of the solar corona. And sometimes due to this kind of solar flares, large chunks of plasma are thrown away from the sun, and then these chunks of plasma, it's again, where is this here? here, this one. So these chunks of plasma move away from the sun in the form of what are called coronal mass ejections or CMEs. So I may mention that this image of CMEs, video of images CMEs, is taken with a space coronagraph. So a coronagraph is an instrument in which we create an artificial eclipse inside the telescope by blocking the sun's disk. But at the sea level, there is so much scattered light that even when you cover the sun's disk, you may not be able to see the corona. But when a coronagraph is flown into space, you can see the solar corona continuously, and you can observe these kinds of CMEs. And looking at the CMEs, you get a feeling that there is some kind of an outward flow from the sun which is scanning the CMEs outward. And this outward plasma flow is known as the solar wind, which was first predicted by Parker. And we know that the Earth's atmosphere is held to the Earth by the Earth's gravitational field. So you can think of what happens if the atmosphere becomes much hotter, like 500 degrees Kelvin. So then we know that all living beings will perish, but this atmosphere would extend much more against the Earth's gravitational field. So Parker realized that the sun's temperature is so high that sun's gravitational field will be unable to keep the hot corona confined. So he derived this result that there will be a plasma outflow, continuous plasma outflow from the outer regions of the solar corona, which he named solar wind, and he calculated what should be the density and velocity of the solar wind near the Earth's orbit. So at that time, most of the astronomers thought that it was a completely absurd idea, but within 3-4 years of this prediction, the solar wind was discovered in situ by space missions, and the density and velocity of the solar wind near the Earth's orbit were found to be basically like what Parker had predicted. So this is regarded as one of the triumphs of theoretical solar field, one of the triumphs of theoretical astrophysics. And you know that the light takes about 8 minutes to cover the sun-Earth distance. But on the other hand, the solar wind takes about 3-4 days to cover this distance. That is why after a major solar disturbance, often its effect is felt in the Earth 3-4 days later. And here I show what is known as Earth's magnetosphere. So if the Earth was sitting in an empty space, then the Earth's magnetosphere would have looked exactly like a dipole magnetic field shown in electromagnetic theory textbook, but the solar wind impinges on it and squeezes the magnetosphere from one side and spreads it out in another side. So when coronal mass ejections impinge on this boundary of this magnetosphere, that's when various effects are produced on the Earth. Now, in a particular scientific research field, it may have a special aesthetic and intellectual appeal if we can show that various phenomena in the field are connected to each other through some unifying concept. And that is certainly the case in our field. So our magnetic field of the sun is the unifying thread which connects various solar phenomena. So firstly, this dynamo process in the interior of the sun produces this magnetic field, and then due to magnetic buoyancy, it comes to the surface and produces sunspots. And due to currents in the magnetic loops above sunspots, we have production of heat leading to the hot corona, and eventually the hot corona drives the solar wind. So one remarkable fact about our field is that virtually all the links in this chain of causes and effects were discovered by one single human being, Eugene Newman Parker. So he formulated dynamo theory, he gave the idea of magnetic buoyancy, and he showed how heat is produced by currents in the coronal loops, and he predicted the solar wind. So I had the privilege of doing my PhD thesis under his supervision at the University of Chicago. And some of you may know that while he was still alive, NASA sent a mission, Parker Solar Probe, to study the very hot regions of the solar atmospheres. And this was the first time that NASA named an important space mission after a living person. So here I show a photo of this building, Laboratory for Astrophysics and Space Research in University of Chicago campus. So this corner room was Professor Parker's office, and my office was next to that. And this other corner office on this side was Professor Subramaniam Chandrasekhar's office. So, well, I think since this flow diagram indicating this cause and effect, this chain of causes and effect, that summarizes most of the things which I discussed in my talk. So I shall end here by leaving this chain of causes and effects before you so that you can look at it for some more time. So thank you.
Okay, I think if you have now questions, please raise your hand. So if you have some questions, please go ahead.
Yeah, it's people have understood everything or nothing. There are no questions. Yes.
There is a question from IPR.
Okay.
Hi, sir. It's Joydeep here. Thank you for a very nice talk again. I heard you last time in IPR. I'm again hearing you. Uh, so I have a simple question, very basic, means for a curiosity rather than a question. Mm, like you said in this reconnection thing, when these two magnetic field joins, so there must be a reconnection time, and during that time the those field lines are not closed, so del dot b equal to 0 is not valid. So how we take care of that problem?
Oh, well, that I can we get back to the. Okay, so due to atomic diffusion in the central region, magnetic field lines here may get dissipated, but then this part of the magnetic field line gets connected with this part, and this part gets connected with this part. So there will be not any time when divergence B is equal to zero condition is violated. So it will evolve in such a way that does not is not violated. So that is one of the basic equations of Maxwell. So unless you have a magnetic monopole somewhere in the system, otherwise certainly this equation will not be violated.
Okay, sir. Thank you.
So I have a basic question. Is there a simple recipe to initiate this experiment in fundamental plasma devices, linear machines, like magnetic reconnection type experiments?
Okay, about magnetic repulsion type experiments, I don't know much, but probably I think even in laboratory plasmas, magnetic reconnection takes place. So I can say a few words about this dynamo experiment. So one of the this necessary though not sufficient condition of the dynamo action is that a magnetic Reynolds number has to be higher than one, and which is difficult to achieve in the laboratory. So there was for many years there was this question, this dynamo process which produces magnetic fields of the earth and the sun. So whether that can be reproduced in the laboratory. So about 20 years ago, by doing experiments with molten sodium, for the first time, this dynamo action could be demonstrated in the laboratory. And it's a quite complicated experiment. So as far as I know, that around the world there are probably about half a dozen groups which have laboratory devices to demonstrate the dynamo action in the laboratory. So I don't know that much about laboratory experiments in magnetic reconnection, but I believe that there's evidence for that in various kinds of plasma devices.
Thank you, sir.
Hello, am I audible, sir?
Yes.
Sir, I am from IIT Dhanbad from Geophysics department. Does geomagnetic field of the Earth is affected by the sun's magnetic field?
Uh,
Geomagnetic field of the Earth.
well, I showed uh, this magnetosphere. So this geomagnetic field produces the magnetosphere. So that's why this magnetosphere gets disturbed by the solar wind and the solar disturbances which carry the solar wind. But certainly, the geomagnetic field inside the Earth does not get affected. These parts of the geomagnetic field which are much above the Earth's atmosphere, only that part gets affected. But presumably, what is happening in the sun that does not have any influence on the dynamo process taking place inside the Earth.
Okay, okay. Thank you, sir. Sir, one more question. Is there any contribution of the sun's magnetic field in the generation of the Earth's magnetic field due to the self-sustaining dynamo?
Okay, that is a kind of interesting question. It's in a subtle way. I think it is because could not go into this details of this dynamo theory. But from the dynamo theory, one can show that if you have an initial small magnetic field, then the dynamo process can build up a strong magnetic field out of that. But if the magnetic field is absolutely zero, then dynamo process cannot start. So from where this first seed magnetic fields came, that is also an important question in dynamo theory. So we believe that the solar system formed from the interstellar gas clouds, and we know that such interstellar gas clouds are magnetic fields, which presumably acted as a sort of a seed field for the sun and the planets. So certainly this Earth's dynamo also needed some initial magnetic field to begin with, and that was at the time when it was forming from the interstellar gas cloud. So certainly the seed field arose together. So that would be the connection between the Earth's magnetic field or the sun's magnetic field. But presumably for the continuous sustenance of the geomagnetic field, that happens due to the dynamo process inside the Earth. So for that, you do not need any continuous input from the sun.
Okay. Okay. Thank you very much, sir.
Sir, I am Subir from ISST Guwahati. Hello, I am
Hello.
audible?
Yes, yes.
I am Subir from ISST Guwahati. You saw the sunforce cycle, and I just noticed that the average amplitude is increasing with time. It is right. My
Okay,
observation is
let,
sunforce.
okay, let us. So you are talking about this figure?
Yeah, average amplitude looks like increase with time. And
Oh
it
well,
was
you see that some of the these cycles were strong there, but there is also after that you see that it has been decreased, and in
but
fact there has been a suggestion that that the envelope of this sunspot cycle that follows something called a Gleisberg cycle, which has a period of about 90 years or so. But but the evidence for that is fairly uncertain, because we could have draw a conclusion about the Gleisberg cycle only if we see at least of the order of 7-8 cycle. So here we have barely an indication that there had been such Gleisberg cycles or not, but it's very tentative. It's yeah, some people have suggested this, but we don't know whether it's a reliable suggestion or not.
another thing, being an experimentalist, actually for doing magnetic reconnection experiment, we need a magnetic Reynolds number much greater than 1. Can we produce such plasma in laboratory and do the experiment in laboratory?
Well, since you are an experimenter, whereas I'm a theorist, you would know better than me. As I mentioned, that these dynamo experiments were done with molten sodium, so where the magnetic Reynolds number could be made a little bit larger than 1, but probably not significantly larger than 1. And in other plasma devices, yeah, I don't know. Presumably, there's this magnetic Reynolds number 1 or 1 can come close to that. But in your experiments, what sort of magnetic Reynolds number do you get?
Uh, in my experience, this is much less than 1. I did not calculate, but it will be much less than 1. Okay, okay. Thank you, sir.
So, sir, in the intense laser plasma interaction, there is a huge, plasma and high magnetic field.
Yeah.
Can this uh, magnetic reconnection theory can be verified in that intense laser plasma interaction?
Okay.
Yeah. But
Yeah, thank you for pointing that out. So I also don't know much about this subject, so I also maybe try to learn more about this. So thank you.
More questions? Or otherwise, I will ask the PSSI site.
If there are any more, yeah, this.
So how to unshare this?
Just stop sharing. Okay.
There is a hand raised from PRL, USO PRL.
Okay, yeah.
Any questions from USO PRL? One hand is raised.
Yes, so what is the question?
Uh, 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 it is from he has not written anything, but there is a hand raised.
Okay.
Any questions from USO PRL?
Yeah, actually, can you hear us, Arnab? This is Ramit from USO.
Yeah, I can hear you,
Uh, 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 Very good.
but I'm embarrassed to see you because it was meant for more students, not people
No,
like
no,
you.
no.
But anyway,
We actually enjoyed it very much, very thoroughly. We enjoyed it, and we had all the audience here. Now they're leaving one by one because there is a tea outside.
okay.
So, my question is very simple. That in view of the success of this flux transport dynamo, is there still any chance that the Parker's original turbulent dynamo theory has some merit?
Oh, certainly it has a merit. So, for example, the Earth's dynamo more or less works the way Parker envisaged his dynamo process. Only for the case of the Sun and probably for the other stars, somehow things are somewhat different, and maybe we need a model somewhat different from Parker's model, but still Parker's dynamo work was the starting point of this whole subject, but in the case of the Earth's dynamo, geodynamo, it works more or less exactly as Parker proposed his dynamo theory.
Okay, thank you from myself. And anybody has any question? Okay, thank you, Ananda.
Uh, Hello, sir. Hello.
Yeah, hello?
Hello. This is Jayalakshmi. Can I ask one question?
Yeah, sure.
Yeah. Sir, you told me that the sunspot tilt variations are caused by Coriolis force.
Yes.
Then how we can study the Coriolis force variations in causing this tilt in sunspots?
We know that the sun rotates around its axis as with a period of about 27 days. So in our equations of motions, we just this Coriolis force term, which arises with the rotation, which would be caused by a rotation period of 27 days. So we just put this extra term in our equations of motion, from which in our mathematical calculations the Coriolis force is taken account of.
Okay, sir. Sir, is there any indices or we can study the effect of Coriolis force?
Effect of Coriolis, I don't exactly mean. So all around this we see effect of this Coriolis force. Even in the Earth's atmosphere, you know that these various wind systems, instead of in the north-south direction, you know that this monsoon winds that comes from southwest or the northeast, because this is deflected by Coriolis force. So all around we see effects of Coriolis force. And basically, I would I would point out that the Coriolis force is effective only on systems which have a time scale comparable to the rotation period. So, for example, in the case of the Earth, you will see the effect of Coriolis force, and if the for something of its time scale is of the order of 24 hours. So large scale ocean currents and flows in the atmosphere, they are affected by Coriolis force. But if you have something like a waterfall in which or a small portion of the river where the time scale of water flow is of the order of a few minutes, then you will not see the effect of the Coriolis force. So, but if something is a dynamical time of 24 hours in the Earth, then you will see the effect of Coriolis force. And in the Sun, if something has time scale of 27 days, then you will see the effect of the Coriolis force.
Yes, sir. So, how can these irregularities in sunspot cycle, whether it is possible due to this Coriolis force variations?
No, these irregularities are not due to Coriolis force variation.
No.
So these
Okay.
irregularities are, as I said, that there is another aspect of dynamo theory, how this colloidal field is produced, which is somewhat more complicated and technical. I did not get into that. So it's
Okay.
basically, we believe that due to fluctuations of in that process, that these irregularities are produced.
Okay, sir. Thank you so much. Thank you so much.
Okay, if there is no other question, so I will ask Ramesh da, from the PSSI side. Ramesh da, uh, if there is no
Yeah,
other question,
just a
from
minute.
your side.
Just a minute. 1 minute. Uh, yeah. Can you hear me?
Yes.
Yeah. Sorry, the live streaming thing is not, so I had to put on my laptop. So first of all, thank you, sir, for this wonderful talk, and I hope it is very fundamental, and I presume that it will benefit many of our younger colleagues uh, and students, and also students who will be coming, because we are going to put this on YouTube live for, I think, a few decades. So we hope that this will be a stepping stone for many of the youngsters who want to work in astrophysical and space plasmas. So I think on behalf of Plasma Science Society of India, we would express our gratitude for giving this wonderful talk, and I'll hand it over to Amulya Da for the final words. Amulya ji.
Okay, Namaste. Uh, on behalf of PSSI, I once again thank you, sir, for this wonderful talk. And with this, we will continue with this kind of sessions in future also. And I'll also look forward to get questions from the viewers on PSSI email. If I get questions, I'll get back to you, sir. And thank you again, sir. And if you have any feedback to us, kindly write to us also. We'll definitely work upon that, sir. Thank you very much. Animesh?
Okay. Yeah.
Sir, you have any words to say for towards this talk?
Well, no, it was a pleasure giving this talk, and I can only say that that this is a field in which lots of exciting things are happening, both in